Okay, so this video is going to cover 4.4 notes. Since I can't be in class, I feel like the best way I could get to you guys is through this video. So I wrote out some notes, and I want you guys to take a look at these. 4.4.4 should get you through the homework over the weekend, and I will see you in class on Monday. So the outline that we have for this, I gave this to you via School Loop earlier, right at the beginning of the semester. So far, we've gotten through 4.3. Then we had a quiz. That should have been done in class on Tuesday. Um, but that I'll have those graded when I come back to school on Monday. So this we're going to cover 4.4 theorems about zeros of polynomial functions, and really it's the fundamental theorem of algebra. That's the big one that I'm going to cover here. The fundamental theorem of algebra, excuse me. So the notes that we're going to have on that is here. I typed some of the things up, so what you should have in your notes should reflect really everything from here down. You already have this in your notes. You already have all this written down from 4.1. So if you need to go back and take a look, you can. But honestly, I just wanted to just rehash and recall this information just before we got to the fundamental theorem of algebra. So what we're looking at is the standard or general form of a polynomial function. So here it's this big gross looking thing. F of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus, and then there are a whole bunch of stuff in between because we don't really know what n is, so we have to have some spacer here. And the last two are going to always be a sub 1 x to, and it's really the first, plus a sub 0, right? Where there is no x, or x to the 0, x to the 0 power is really 1, right? So that's why we don't put x there on the end, and that is our constant. All right, so what did we get out of that, right? We have our key characteristics that we can see. Just in that form, what we get is the leading coefficient, and that is our, try and be quick about this, that is our a sub n, right? So just a sub n, the number in front of the variable with the highest exponent, and the variable with the highest exponent tells us the degree, right, which is simply the highest exponent. It's just n. This also tells us right here, we now know that we could look at comparing those two things, and we could talk about end behavior, right? What's happening at the tails? So to the left and right, is it going up and down? Or, there's a combination of that we saw on that chart that would help us. And it also helps us graphing polynomial functions as well. And we also know the constant. All right, so the constant is simply this guy here, the last one. The constant can be 0. So for example, here, the constant we see here is negative 48, but if negative 48 were gone, there is no constant, right? But we definitely want to have that negative 48 for the example. So that would be the constant. That a sub 0 or negative 48 would be that number. My a sub 1 is 80 because it's x to the first. And here we take a look at the very first one. This one gives us the majority of our characteristics here. So 2 being my leading coefficient, a degree of 4. I know with the end behavior, both to left and right, they're both going to be pointed up, right? So I have an even degree and a positive leading coefficient. So that's basically what we get out of that. All right, so now let's go check this out. What exactly is the fundamental theorem of algebra? So this is really where your notes should start. The fundamental theorem of algebra. I did all the liberties of looking it up for you. And yes, I use Wikipedia. Most mathematicians that govern Wikipedia for mathematics are either doctoral candidates or doctors themselves, so I trust these things. And I like how it says it here, not to be confused with the fundamental theorem of arithmetic, which who knows what in the heck that says. All right, so the fundamental theorem of algebra, it states that every non-constant single variable polynomial with complex coefficients has at least one complex root. Okay. So this, let's see. This is the fundamental theorem of algebra as is. And let me just add the space here. Okay. So it says, the fundamental theorem of algebra states that, here I can get rid of that. It says, every non-constant, so if it looked like this, oh no, that would be a constant function, right? Because it just had the constant. So every non-constant single variable, okay, so what it means is just on the right-hand side, not this y equals, but just the right-hand side, the variable is just an x, right? Even though it has these exponents here, there's only an x. It doesn't say x, y, z, or w, or any other variables here. It's just an x. So single variable polynomial, which we've discussed this is a polynomial, has complex coefficients. Well, this doesn't say 2i, x to the fourth, or 5 plus 1i. It doesn't say anything like that about these. These are all real coefficients. So that's kind of interesting. We'll have to investigate that. Has at least one complex root. So this tells me that I have at least, so I could have more. I could have more complex roots, but I have at least one complex root. Boring. So really, what is it saying about what is the root? Well, the root is the same thing as, where does it go? Excuse me. The root would be the same thing as an answer, right? The root is an answer to, not an answer, but an x value that satisfies something like my son's aunt just got here. That's funny. So if you hear a weird voice, it's her. Okay, so a root would be an x value that satisfies this equation, right? 0 equals this. Well, really what I just did is I said, I replaced, so I literally, I replaced f of x with 0. So isn't that the same thing as a 0, right? 0 of a function is an x value for which f of x equals 0, right? So now that basically tells me that a root and a real 0 are the same thing, right? And it's also known that, it's also known that a root and a solution are considered to be the same thing. So really we have 5 words now. We have 5 words that really imply the exact same thing, right? We have 5 words that imply the same thing. We have root, solution, 0, x-intercept, and a root, a 0. No, just the 4 things, excuse me. So those are all, in general, they're all the same thing. All right, so let's go back to the fundamental theorem of algebra. The fundamental theorem of algebra, this guy, no. This guy, nope, not that one. This guy, man. Right? The fundamental theorem of algebra, what it really says is, if I have a polynomial function, I have at least one complex root. Well, let's go back and read this for a second. Let's read on. It includes polynomials with real coefficients. All right, so we have a polynomial that has a real coefficient. And here's why. Every real number is a complex number with the imaginary parts being equal to 0. We already discussed that. We already knew that. So what this whole thing really tells me is I have at least one answer. I have at least one 0 for every function. Well, it's been widely stated and proved in the history of this problem. And in fact, you really should go read it. Not that. Right, you should go read this. The beginning here is really, really interesting. So just this paragraph would probably be of major interest in the history of the fundamental theorem of algebra. So, okay. So the takeaways we get for this are, we have four big takeaways. Number one, n is the number of solutions to this. So if I have a degree of 4, then I have exactly 4 zeros. So we can say then that the degree and total number of zeros are equivalent. So that's really good. That helps me when I'm that's the big part. I mean, that helps me when I'm solving these problems, because here in a second we have to find all the zeros for this function, and I know that the degree is 4, so I'm going to have exactly 4 zeros. So that's helpful information. It's really helpful. What else? We know that real zeros and x-intercepts are the same. Right? Again, emphasis on being a real 0. Right? So that then tells me that zeros can be real or complex. Really, we've discussed every single one of those items in class already up to this point, which makes the fundamental theorem of algebra a little silly. It makes it seem really insignificant, but in the bigger picture of mathematics, it's actually really, really, really fundamental. It's huge. Okay, so now how are we going to use this information? How does it help us? So the problem that we're going to take a look at here, find all the zeros for f of x equals 2x to the fourth plus 5x to the third plus 29x squared plus 80x minus 48. All right, so let's go over the steps it's going to take in order for this to happen. One, I want to graph and identify any real zeros. Okay, so if it's an even degree polynomial, there's a chance that I don't even have any x-intercepts. Step 2, we want to, on the second step, we want to confirm with synthetic division. And number 3, the third thing we want to do is solve the remaining quadratic. All right, so we're going to be able to take away, so here we have x to the fourth. We're going to get all the way down to x squared, right? A quadratic where it's x squared. So in order to do that, we have to take away 2 of those with synthetic division. All right, we're going to finish this problem on the second video here in just a few minutes.